Hey folks, my name is Robin and I work at Poolside, as indicated correctly. Today we'll talk about how we went from a very sort of ad hoc system that came about organically to something that is a sort of well-formed distributed system that is easy to understand and that gives us the ability to churn out many models in a given week. To start off with, I'll give you a walkthrough of a new feature that we developed last week as a sort of example of how people will interact with the system. And so to kick us off, I'll give you my favorite statistic, or I should say least favorite statistic, because we're building agent models, and these are good models. They they edit code, they can do that over long time horizons. But it turns out that when we introduced the to-do tool, it just wasn't really interested in using it. And there was not much we could do to convince it to do otherwise. And this is somewhat surprising on the surface because you'd assume that it will increase performance, so it should want to use it. But the more that we dug into it, it turns out that the to-do tool does like two different things. Like one, it gives the model a way of keeping track of what's going on, and two, it gives the user an idea of what's happening. But even when you look at the models that were built in the outside world that are using the same tool, the actual performance bump you get is not that big. And so if you're relying on reinforcement learning to get this tool to be used frequently by this model and correctly, we basically had to do something else to get this to be like a reliable part of our model behavior. And so when we had a new engineer join our research org recently, we felt like this was a good example to give him a way to try out the different ways to improve our models. So the first step is obviously evals. The last talk ended on evals. So we try to understand exactly, maybe we can prompt it, maybe it struggles to use the tool, we change the implementation. And when we looked at the data, it was, we're looking at single-digit percentage of trajectories using the to-do tool at all. At all and correctly, only 5%. The prompting only changed single-digit percentage of the trajectories. With really strong prompting, you could get it to do more, but it would still not really, use it in the way that you'd want to. And so we needed a bigger hammer, effectively, to change this underlying behavior. And the way that we do things is that we'll basically look at the easy things to do, and we'll do those first. So the easy thing is, how about we just dial the reward for this tool to 11? And this is the sort of first bit of how our model factory is exposed to our researchers. Everything is in Python. And in this case, we introduced a new reward that just goes massive amounts of reward if you see the to-do tool at all at any point in the trajectory. And because obviously dialing it to 11 only would not necessarily, you wouldn't expect it to work super well, we trained, our researcher basically trained 4 different models with one PR. So one PR, 4 different reward structures, feeding into this RL kind of training process. And then out comes this kind of asset, which we view in our central UI. So we have a single pane of glass where we see all of our experiments, all of our data sets. And then with a click of a button, you can kick off the training process. And this will do the kind of thing of hundreds of GPUs for multiple days. And after that has completed, we ended up with multiple models that use the to-do tool more, which is yay, success. But one of the interesting things here you can see is that if we only had tried maybe less reward, or we had tried it for less long, it wouldn't have actually increased the correct usage. And this is ultimately the thing that people care about. And so this ability to train multiple models with different characteristics and then compare them was really helpful here. And that only took 2 or 3 days. And once we had a model that was sort of behaving correctly, we've played with it, the evals look good, we then deployed it internally to our extension, and then we have internal dog fooding. And this is also one example of something that we believe very deeply, which is that most capabilities will ultimately fall into the model. We expect our models to be able to use something like a to-do tool, instead of bolting on UI kind of elements and summarizing bits of what's going on to kind of fake the to-do view. Cool. So how does this kind of workflow actually work? We started about 2 years ago, and in this process have scaled up multiple times by quite a lot. And anyone who starts in this space will basically start sort of in this area here. You've got just some ad hoc scripts, maybe got some Jupyter notebooks. People love Jupyter notebooks. And then you have like data being shuffled around and ultimately pushed into GPUs. But as we got more and more data and more complex training experiments, it became very difficult to understand what we even fed into models, or it would be very kind of expensive to trace back exactly which changes in our input training data we were using. And also, we gained more scripts. So both we have more data and it's difficult to trace it, and also more complexity to run a single training run. And so we went from that to a sort of coherent model factory vision. We had hired enough distributed systems engineers to look at the previous state of the world and sort of go, oh God, let's definitely change this, which is exactly what the thing on the right is looking like. This doesn't render super beautifully. The main thing that we changed to was a directed acyclic graph in a platform called Daxter, where every experiment and every data set is defined in one graph, and so you can always trace back exactly which bits of data went in. It has the whole kind of history, and you can see who edited it, etc. To make this work, you need many boxes, approximately this many boxes. And once you've recovered from your sort of cognitive overload from being shown a very complicated diagram, this will be the map for the rest of the talk. The kind of UI part that we're looking at is sort of a mix of the bit at the bottom and a bit on the right. It's kind of the coordinating view portion of the system. And as we go, I'll just walk you through this from the left to the right. So you've got sort of inputs to this model building process, which is data sets, synthetic data, etc., filtering and transformations. Then you've got the core training process. This is the part that actually uses all the GPU hours. And then you've got the post-training stage. You've got a base model, but you want to make sure it does has specific behaviors. And this is where we have reinforcement learning, where we have lots of manual inspection things to figure out how we need to tune the system. OK, let's have a look at the next layer of abstraction that a researcher would look at. We saw earlier that there is some Python involved, but we have a very strong belief that everything is in code. We don't have config files as such. A researcher will define each of these nodes in this graph with Python functions. And this is the basic shape. You've got a bunch of resources, for example, a Spark cluster, and input data frames that are being fed into a function that then makes some transformation and returns a new data frame. And the key part is that each node in this graph is immutable. So you click a button, there's no like appending. You don't need to like divine when someone might have clicked the button again. It just does a snapshot of the world, exactly one instance. It's immutable until a regeneration occurs. And then you have a graph of these changes. The fact that you have this in Python also means that you might want to make, as we saw earlier in the example, you might want to make multiple model instances or training runs that differ in maybe a few different axes, which is commonly called ablations. And this is easily done with Python as well. Again, I mean, this is just a Turing-complete language. It can do whatever you want. In this case, you can create multiple instances of the same pipeline, and out comes an asset with multiple instances of a model, which can be either materialized together or one at a time, whatever you want. Now, the next stage here is that the content of your Python function kind of matters. And the thing that we have built around Daxter is a sort of framework level that handles the coordination with the rest of the system, and in particular, loading and storing data to our data lake, which is backed by Iceberg and S3. And once you have the data, it'll do things like manage inference and RL processes, and make sure that the kind of plumbing between these different systems functions. And so this is kind of the arrows here. There is a task engine on this diagram as well on the right. It's basically a Python framework for feeding data between different systems and managing the resources under the hood. And the thing that it communicates on a systems level, so these are distributed services, is a scheduler. So the scheduler here is responsible for, you say, I want to have maybe 1,000 GPU days worth of RL happening. The scheduler is then responsible for making sure that this is going against different resource groups in the company. We've got 10,000 H200s. This is enough that you need sophisticated planning and scheduling and so on. You want to make sure that researchers don't spend their time micromanaging exactly who gets which GPU and like for how long, and making sure that their runs start at the right type and so on. So we basically just schedule these jobs, and then they get scheduled on the cluster when they're ready. And as the sort of GPU resources are being spun up, you'll get access to like evaluation endpoints, reinforcement learning, et cetera. They all hang on these like the inference or training capabilities of these GPU workloads. Okay, cool. So let's imagine for a second that you've gone through this thing and you click buttons on some pretty UI. The next thing is that you're probably setting something like $100,000 on fire. You need to understand what you're actually doing. How is your run progressing? And there are multiple components. We have sort of system metrics in Grafana. This is for our code execution environment. So there's like something like 10,000 concurrent agent runs there. But to make this a bit more interesting, this is an inference snapshot, throughput snapshot as part of an RL run. And it was in particular part of a training run where we were trying to make this thing faster. Even if you have a lot of GPUs, you always want to make it go a little faster. And here it's going 3 times faster. It's amazing. Look at it. So this all looked good until we look at the other platform we use for data, which is training specific. And here we have basically everything that you as a researcher want to see. So you want to see the red line. The reward is going up as time progresses, as does success rate, as defined by our RL tasks. But then in the second row, you see very, very different behavior, especially in the blue lines. And each of these lines is a different experiment. The blue line corresponds to this like much higher throughput environment, and it was an experiment with additional caching. And the second line basically showed, okay, we have a massive issue here because we have a very large divergence between our RL task generation and the training process. They don't agree on the updates that they should be making. And here we see the reward is also decreasing. So like RL is not completely broken, but it's not in a good state. And what this kind of view led us to do was to basically dig into exactly what's wrong at the infrastructure level. And as with all things, it comes back to boring reasons. In this case, we were not invalidating caches correctly. Yeah, that was expensive. Anyways, okay. So the way that you can run these large experiments and kind of dig into the kind of problems that this is an example of is that we have like a large history of training runs, and then you can compare it against like both the multiple arms of the experiment, but also against maybe an experiment from 3 weeks ago. And when we had this particular issue, we also actually started running experiments from a few weeks ago just to make sure that we hadn't changed something else that was amplifying this effect. Cool. The next big piece that we have built is a system to support reinforcement learning from code execution feedback. This is reinforcement learning on top of LLMs is obviously all the rage at the moment. And this is something that we've started working on at the very beginning of the company. The core premise is that you can only get so far with just doing next token prediction. You're going to eventually need another source of data, because we're all training on the same internet data. So code execution gives you a really nice sort of line of sight to a solution for generating a lot of examples with reinforcement learning for code editing in particular. So this is the kind of, we're seeing a massive boom in this area right now. And we've been building this like large-scale execution platform, which like at a first approximation, you can model this as a like large, I don't know, containers in the cloud sort of thing. But we needed to have very, very high throughput. And we needed like low latency as well. So we basically ended up with a system that supports millions of repositories and tens of millions of revisions. And you might imagine the mild sense of shock you're going to get if you ask a sales rep at AWS to store 100 million containers for you and get them fetched really quickly. The thing that this allows us to do, that we have a system that can do this, is that we can get more training data and also now have our agents run in these sandboxes. So when it became clear that our model was actually performing really, really well across multiple steps, we were like, I think it took us like a week and a half or 2 weeks or something to go from running a few things that do, tens to hundreds of steps to then having 10,000 things do that and then kind of kicking off that process. The code execution environment is also obviously has like isolation boundaries for security. If you don't have security across running like completely untrusted code, you're going to have a bad time. And so aside from having very strict network kind of restrictions, we actually built this entire thing on top of the kind of low-level kernel abstractions rather than something higher level. So we use like things like run C and so on directly, and that gives us very tight control over anything from like the block devices to the network stack. And also, I don't know if you've seen this in recent coding models. They're also all trained with RL, and they will attain certain behaviors that might not be desirable, like declaring the job done before it's done, or just deleting all of your tests and this kind of thing. And having this like control over exactly which files are even accessed or which are read and so on has been really helpful for us to put an end to this sort of, I don't know, I put down here high school behavior. Just delete your tests, say it's done. We had to at some point download things from github.com. Amazing. Cool. So that's it. We've got a code execution platform. There's many sandboxes. It's what we're using for our agentic model development. This whole system has been in the works for a long time, and it's really like amplified how quickly we can push out models. And it allows like engineers and researchers to like focus on what actually matters, which is not just the system bits, but also building more models and doing so faster. So this prepares us for like more compute, more GPUs, more data, and we're already seeing like for 10x the data throughput. This is not a big issue for this system. Cool. If you found this interesting, this is taken in part from a blog post series called "The Hidden Engineering Behind Foundation Model Building," which we have on our website. And if you want to chat about this or you want to lend us a hand, my email's here, robin@poolside.ai. Thank you very much.
Thank you. Thank you, Robin, for this talk.